This is the last video on the complex numbers chapter, so it finishes off the first chapter of Further Maths AS, and this is on cubic and quartic roots. So we've done quadratics in the last video, so this is cubic and quartic. So obviously this opens up some more options. Cubics, we could have potentially 3 roots, so 3 real, maybe 1 real, 2 complex, mixture of repeated roots and stuff like that, but we can still get our complex roots. And there's a few little notes for you to look at, so make sure you read through them. And then with a quartic, there's even more roots available and more options available. So make sure you read through the notes on that to give you an idea of what's going on. And we'll go straight in with the questions on this. So number 1, we're given that -1 is a root of this equation, so z cubed minus z squared plus 3z plus k equals 0. So given that -1 is a root, find the value of k, find the other 2 roots. So if -1 is a root, that means it is a solution to this equation. So that means if I put -1 in for z, it will work. And I've just got a nice equation to solve. So we get -1 cubed is -1, -1 squared is 1, so this will be -1, 3 times -1, so we get this. -3 minus 1 is -5, add 5 to both sides, and we get k equals 5. So that's part A. Something is a root, sub it in, it will work. It's a solution. So find the other 2 roots of the equation. So if z is -1 is a root, then that means z plus 1 is a factor, using our factor and remainder theorem, which we should have done either in the Further Maths GCSE or in your A-level maths. If not, then you can ask and go through it. That's fine. But that means z plus 1 is a factor. So there's 2 ways of doing this. Either I can do long division. So algebraic long division. Sorry, that was just annoying me. There's a big space. So either we can do algebraic long division, or we can do our equating coefficients method. It's good to be both good. It's good to be good at both of these, is what I'm trying to say, because then you've got different strings to your bow. So if z plus 1 is a factor, we now know that k is 5, so we know that our polynomial is z cubed minus z squared plus 3z plus 5. That's our equation. So using division, and because we know z plus 1 is a factor, that means if we divide z plus 1 into this, we'll get no remainder. And remember, always leave a column for every power, so z cubed, z squared, z, and then the constant. Even if there's no z squared term, make sure you leave a column for it when you're doing this. So we take the z and we divide it into the z cubed. So z into z cubed goes z squared times. So we stick that on the top, and then we're multiplying both of these by z squared. So z squared times z cubed is z cubed. Z squared times 1 is z squared. And subtract, z cubes cancel. Minus z squared minus z squared is minus 2z squared. The 3z and the 5 drop through. And then we do the same, z into this, which is minus 2z. And then multiply minus 2z by both of these bits. So minus 2z squared minus 2z. Subtract. Minus 2z squared minus 2z squared cancels. 3z minus 2z is 5z plus 5 carries through. Z into 5z goes 5 times, so plus 5 times by that. So 5 times z, 5 times 1, as expected, no remainder, and therefore we've got our quadratic factor. So therefore this cubic can be written as z plus 1 multiplied by the quotient, which is the answer we get in here. And if we solve, we know that this one gives us 1 root, -1. We knew that because we knew -1 was a root. We told that in the first place. and then the other roots will come from this. So let's complete the square. It's quadratic, complete the square. Z squared minus 2z, take the 1 away as surplus. So we're going to get plus 4, subtract. So we're going to get complex roots, but we can now square root this. So we get plus or minus root minus 4. So root minus 4 is root 4 root minus 1. So this will be 2i. So we'll get z is 1 plus or minus 2i. So therefore my 3 roots are minus 1, 1 plus 2i, and 1 minus 2i. And we can use our calculators to check this as well, and we can sub them back into the original to check as well. There are 3 roots. Again, notice when we've got real coefficients, we get some sort of, if there's a complex root, we will get a complex conjugate pair as 2 of the roots. In this case, 2 real roots, 1 real root, 2 complex roots. Graphically, it's going to look something like this, where there's our minus 1, our real root, and then it doesn't intersect again here, no intersection down here, because we've got complex roots. So that's doing it by long division. If you want to equate coefficients, then we know that if z plus 1 is a factor, then we must times it by some quadratic to get our cubic. Like this. And then by inspection, the only way of getting an x cubed term is the z times the az squared. So a must be 1. And the only way of getting the constant, the 5, is the constant times the constant, 1 times c. So c must be 5. So then we can fill in those parts. And then either you can match up the z squared terms, or you can match up the z terms. Let's equate the z terms. So they must be the same on both sides. So on the left, our z term comes from the z times the 5. So 5z. And the 1 times the bz, which is just bz, and that must be equal to the z term on the other side. So the coefficients must match up. So b must be minus 2, and therefore our quadratic factor is a z squared, a is 1, plus bz, which is minus 2, z, plus c, which is 5. So there's our quadratic factor, which matches up with the quadratic factor in here, and then we would just solve it in exactly the same way, and you get your 3 roots exactly the same. That's it. So cubic, we've got 1 real root here, 2 complex roots. We can use algebraic long division to get our quadratic factor. We can use equating the coefficients to get our quadratic factor. We can complete the square to solve. We could use quadratic formula to solve if we wanted to. Obviously, if it was all 3 real roots, then it would factorize, or you'd get real numbers with your quad formula. But most of these questions are going to involve complex roots because that's what we're looking at. Pause the video at any stage if you need to. It's a slightly longer question. But 2 different methods. Learn how to do both. It's nice to have different routes to get there.